We previously saw that when we wish to compare the means for two populations, we can use the two independent samples t-test. For example, in a different video, we used the two independent sample t-test to determine whether there was a difference in expressive language skills for 7-year-old children with hearing loss based on whether they were diagnosed by 3 months of age or diagnosed later in childhood. But what if we want to compare more than two populations? For example, let's say I want to determine whether there's a difference in expressive language skills based on the degree of hearing loss a child has. Specifically, I want to compare children with clinically defined mild or moderate hearing loss with those who have severe hearing loss or profound hearing loss or progressive hearing loss, where the degree of a child's hearing loss increases over time. Now, in this case, I got 4 groups. I guess I could do half a dozen t-tests comparing each group to each other group, but that's not very efficient. And if you think about it, if each of those t-tests has an alpha level of 0.05, those 5% chances of committing a type 1 error start to add up until we're inevitably reporting something that's just random chance. This is where the analysis of variance, or ANOVA, comes in. For now, we're focusing on a specific type of ANOVA, the most basic, that's called a one-way ANOVA because it involves a single predictor variable. So the purpose of a one-way ANOVA is to compare the means for 3 or more populations. Now, you can perform an ANOVA with only 2 samples, in which case you'll come to the exact same conclusion that you would have if you simply did a 2 independent samples t-test. Plus, as we'll see later, the results for the 2 independent sample t-tests are more easily interpreted than the results for the ANOVA. So if you have 2 groups, do a t-test if you've got 2 groups. 3 groups or more than 3 groups, do the ANOVA. Now, as always, there are a number of assumptions that need to be satisfied. First, the outcome variable needs to be normally distributed in the population. Again, if the sample size is large, this becomes less of an issue. And also for ANOVA, if the groups are all the same size, this becomes less of an issue. ANOVA is kind of more robust when all of the groups are the same size. They don't have to be, but it's handy with ANOVA if they are. The outcome variable also has to be on an interval or ratio scale. There's other tests available if it's not. The samples need to be independent, like with the independent samples t-test. Scores in one group can't be linked to scores in the other groups, such as repeated measurements of the same person, or different members of families, such as the mom here, the dad in that group, and children in another group. No, it needs to be independent. In addition, we assume that the variances of the populations being sampled are equal, which should then mean that the variances for the samples are fairly similar. Looking at the variance in each sample, a rule of thumb is that the largest variance should be no more than twice the size of the smallest variance. Finally, let's note the importance of the samples being representative of their population. We're ultimately trying to estimate features, means, and variances of these populations. If our samples don't accurately reflect the population, then our conclusions won't be valid for the people we want to talk about. That's why we like random sampling. it helps us to ensure that the sample does in fact reflect those population characteristics. Now, if the data satisfy these assumptions, you can then work on formulating your hypotheses. Now, with the two samples, right, we could have hypotheses that the mean for one population is greater than the other, or less than the other, or different from the other. But with 3 or more samples in a one-way ANOVA, the possible scenarios is much more complicated than that. I mean, think if we've got 4 different groups from 4 different populations, A, B, C, and D, maybe A and B and C and D are all different from each other, but maybe not. Maybe A is higher than B, but maybe A is a lot higher than C, but B is only a little higher than C, and maybe C and D are exactly the same. And that's just one way that the populations may differ. So a one-way ANOVA addresses this complexity by simply having a single option for your null hypothesis and a single option for your alternative hypothesis. Yes, you heard correctly. There's just one. The null hypothesis is always that the means for all the populations being studied are equal. Mathematically, that's just mu1 equals mu2 equals mu3 equals on and on up to mu k, if whatever k number of groups we have for k different populations. And the alternative hypothesis is that the means for all of the populations are not equal. Now, note that this doesn't mean, no pun intended, this doesn't mean that every mean has to be different from every other mean. It only means that at least 2 of the means are not equal. For example, you might have means of 50 for one group and 50 for another group, and then 20 for a third group and 80 for a fourth group, with only the third and fourth group being different from each other. Now, you may sometimes see the alternative hypothesis written as mu1 doesn't equal mu2, doesn't equal mu3, doesn't equal mu on and on up to k. But if you think about it, that's not correct. Because mu1 could be equal to mu2, but not equal to mu3. So you can't write it out that simply in a mathematical equation. Now, returning to our example based on children with hearing loss, our null hypothesis would be that the mean expressive vocabulary score for children with mild or moderate hearing loss is equal to the mean for children with severe hearing loss, is equal to the mean for children with profound hearing loss, which is equal to, catch my breath, the mean for children with progressive hearing loss. Our alternative hypothesis would just be that all of those means are not equal, right? At least one is different from the others. Maybe more than one, but at least one is different from the others. So how does an ANOVA work? Now, remember, with the z-test and the t-test, we looked at how big of a difference or effect did we observe, divided by how big of a difference or effect did we expect. The how big of a difference did we see was the difference in means. The how big of a difference did we expect was measured with our standard error. But that doesn't work with ANOVA. I mean, how do you get a single number that describes differences or expected differences between 3 or 4 or 7 or who knows how many different groups? We do it by looking at variances instead of just looking at the means. And if you think about it for a moment, that kind of makes sense. Variance describes how spread out our scores are, how spread out things are, which reflects how different things are. If there aren't a lot of differences, the variance will be small. If there are a lot of differences, the variance will be large. The two independent sample t-test examines differences between groups. X bar 1, X bar 2, right? X bar 1 minus X bar 2, what's that difference? Relative to how big of a difference did we expect to see between those means, the standard error of the difference in the means. ANOVA approaches this same general idea, but does it by examining what we'll see is the variance between our group means relative to the variance we expect to see, which is the variance within our groups. Same idea, just different tools because we have more than two groups. Let's look at a visual illustration of what I mean by variance between groups and variance within groups. So to keep things simple, let's say that I'm comparing samples for 3 populations, and I make a graph comparing the distribution of scores in each of these samples. It looks something like this. Now, looking at this, what do you think? Are the population means for these groups different? Remember, these are samples taken from the population, and of course there's going to be some difference between our sample means and the sample distributions, even if the null is true and the population means are all equal. Now, pause the video for a moment and look at this and think that looking at those sample distributions, would you be confident rejecting the null? Would you be confident saying that, wow, based on those distributions, I'm convinced that the means for the populations that are reflected in these samples are definitely different. They're not the same. If you're not comfortable rejecting the null, why? What is it about that distribution that makes you nervous rejecting the null? All right? Pause the video and restart when you've thought it through a bit. Me? I would be nervous rejecting the null with this data for 2 reasons. First, notice the difference between the means, these dashed lines, is relatively small. The variability between our groups is small. That's particularly true when you look at how much variability there is within each of those groups, right? Now, if there's only a small amount of variability between our groups and a lot of variability within the groups, it's easy to see that that small variability between the groups may just reflect that random chance. Okay? Now, in contrast, what if the data looked like this? If the distributions for our samples look like this, what would you think? Would you be more confident saying that the means for the populations reflected in these samples are different? Now, take a look at that, pause the video, and restart when you've got an idea. Now, in this case, I would be much more comfortable rejecting the null. Notice that the difference between the means is now much larger relative to the variability within each group. I mean, in fact, look, 2 of the groups barely even overlap. Pretty good. If the variability between the groups is large compared to the variability within each group, it seems a lot less likely that those differences between group means are just due to random chance. Now, can you see the parallel here at a conceptual level? with what we were doing with z-tests and t-tests. With z-tests and t-tests, we're comparing how big of an effect we saw relative to how big of an effect we expected if the null was true. But in ANOVA, we're going to do it by comparing variances instead of x bars and mu's. To do that, we'll calculate a new test statistic called an F, in which we compare the variance that we see between our groups relative to the variance that we see within the groups. We'll look at what I mean by this and why it works in our next video. All right? See you then.